Tonight, we're going to confront one of the most seductive ideas in the history of human imagination. The dream that someday we will travel at the speed of light, that we'll fire the engines, pierce the darkness between star systems, and arrive somewhere new, somewhere extraordinary, in days or weeks rather than lifetimes. It is the silent assumption underneath almost every science fiction story ever written. But here's what those stories almost never tell you. Even if every technical barrier vanished overnight, even if you had the ship, the fuel, the energy, all of it, even if you somehow reached the speed of light, the journey itself would destroy you before you arrived anywhere. Because the same physics that makes light speed the fastest possible thing in the universe is also what makes the attempt to reach it so destructive. By the end of tonight, you're going to understand why light speed travel isn't the escape from distance it's made out to be, and why the universe fights back harder the closer you get to it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The speed of light in a vacuum is 299,792,458 meters per second. In miles per hour, that's about 670 million. It is the absolute speed limit of the known universe. Not a record waiting to be broken. Not a ceiling assembled from some material that hasn't been discovered yet. A structural feature of reality encoded into the mathematics that describes space, time, mass, and energy. Nothing with mass has ever reached it. Nothing with mass ever will. And the reason for that is not a failure of engineering. It is a consequence of what mass is, what space and time are, and how the three are locked together at high velocities. To understand why light speed travel destroys you, you first have to understand what happens as you approach it. Because the approach alone is already catastrophic. Albert Einstein published his special theory of relativity in 1905. He was 26 years old, working as a patent clerk in Bern, Switzerland. In his spare time, he was thinking about light. At the time, physicists were wrestling with a genuine inconsistency. James Clerk Maxwell's equations, formulated in the 1860s, described electromagnetism and predicted that light travels at a fixed speed. But classical Newtonian mechanics said speeds should add and subtract the way common sense demands. Stand on a moving train, throw a ball forward at 30 miles per hour, and relative to the ground, the ball moves at your throwing speed, plus the train speed. Simple addition. But every experiment that tried to detect the expected variation in the speed of light based on the motion of the measuring equipment returned the same answer. Light always arrived at the same speed. It didn't add. It didn't subtract. It appeared entirely indifferent to how fast the observer was moving. Most physicists of the era assumed the experiments were imperfect, or that some subtle, unaccounted effect was masking the true variation. Einstein did something different. He accepted the experimental result as a fact about the universe rather than an artifact of flawed measurement. He asked, if the speed of light is genuinely the same for all observers, regardless of their motion, what must be true about space and time? The answer shattered every common sense assumption about how the universe works. And the answer was special relativity. Special relativity rests on two postulates. First, the laws of physics are identical for all observers moving at constant velocity relative to each other. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. That second postulate sounds contained. It is not. If light always moves at the same speed from every perspective, then space and time cannot behave the way Newton assumed. They cannot be fixed, universal, absolute. They must bend and flex and distort in ways that preserve the constant speed of light from every frame of reference. This is not a figure of speech. It is a measurable, testable, experimentally confirmed feature of the physical universe. GPS satellites must account for relativistic effects in their time calculations, or their position readings drift by miles per day. Particle accelerators confirm that particles gain effective mass as they approach light speed, exactly as the equations predict. Muons produced by cosmic ray interactions in the upper atmosphere should decay before reaching the ground based on their rest frame lifetimes. They don't, because time dilation extends their apparent lifetime as measured by observers on Earth. The framework is correct to extraordinary precision, and what the framework says about a traveler approaching light speed is clear, specific, and deeply unfriendly to anything biological. The first major consequence is time dilation. Time does not pass at the same rate for everyone. This is not a perception or a psychological effect. It is the actual behavior of time as a physical dimension. A clock moving relative to you ticks slower than a clock at rest relative to you. Not because of vibration, interference, or any mechanical effect, because time itself is passing more slowly for that clock. Every physical process inside a moving frame runs more slowly, as measured by someone not moving with that frame. The amount of slowing depends on velocity, and the mathematical relationship involves what physicists call the Lorentz factor. The Lorentz factor, traditionally written as the Greek letter gamma, equals 1 divided by the square root of 1 minus velocity squared, divided by c squared, where c is the speed of light. At low velocities, the Lorentz factor is essentially 1. Time passes at the same rate everywhere. As velocity increases towards c, the Lorentz factor grows. At 10% of light speed, gamma is about 1.005. A clock moving that fast ticks at about 99.5% the rate of a clock at rest, barely noticeable. At 50% of light speed, gamma is about 1.155. Time passes at about 87% the rest rate. At 90% of light speed, gamma is about 2.3. Time passes at about 44% the rest rate. At 99%, gamma is about 7.1. Time passes at about 14%. At 99.9%, gamma is about 22.4. Time passes at less than 5% the rate it passes for someone at rest. As velocity approaches exactly the speed of light, the Lorentz factor approaches infinity. For something moving at exactly light speed, no time would pass at all. From the photon's frame of reference, if we could speak of one, it is born at its source and arrives at its destination simultaneously. There is no journey. There is no duration. For a massive traveler pushing toward light speed, time dilation becomes more and more extreme. This seems, at first, like a solution to the interstellar travel problem. If time moves slowly for the traveler, you could, in principle, traverse enormous distances in a short, subjective experience. At 99% of light speed toward a star, 40 light-years away, the crew experiences about 5.5 years. The outside universe experiences just over 40. At 99.9%, the crew experiences less than 2 years. Science fiction loves this. It is the part of relativity that seems to help. The problem is everything that comes with it. The second consequence is length contraction. From the perspective of something moving at relativistic speed, space in the direction of travel compresses. The actual physical distance that must be crossed shrinks. Not on a map, not as a subjective illusion, actually shorter, as measured by instruments aboard the moving ship. At 50% of light speed, distances in the direction of travel are about 87% of their rest values. At 90%, about 44%. At 99%, about 14%. The compression factor is the same as the time dilation factor. This is not a coincidence. Space and time are not independent. They are two aspects of a single, four-dimensional structure called space-time. Moving through space-time redistributes the four-dimensional interval between its spatial and temporal components. Moving fast through space means time moves slowly for you. Moving slowly through space means time moves at the standard rate. The total four-dimensional interval is conserved. You cannot have both large spatial distances and fast time simultaneously. The universe trades one against the other, and the trade is described exactly by the Lorentz factor. For the observer at rest, watching the traveler go past, the traveler appears compressed in the direction of motion, and the traveler's clocks appear to run slow. For the traveler, the space ahead appears compressed and time appears normal, while outside time races ahead. Both are real. Both are consistent. Neither observer is privileged. Both are measuring a universe where space and time are not absolute, and both are correct. The third consequence is the one that establishes the absolute ceiling on speed, and it is the one that begins the process of destruction. As an object accelerates, it gains kinetic energy. At relativistic speeds, that kinetic energy doesn't just increase the object's speed, it increases the object's effective mass. This is a direct consequence of E equals mc squared. Mass and energy are not different substances. They are the same thing expressed in different forms. A joule of kinetic energy added to a moving object is equivalent to a tiny increment of additional mass. At everyday velocities, this contribution is so small as to be unmeasurable. But as you approach the speed of light, kinetic energy grows enormously, and so does the effective mass. The relativistic mass of an object equals the rest mass times the Lorentz factor. At 10% of light speed, the relativistic mass is about 0.5% higher than the rest mass. Negligible. At 50% of light speed, about 15% higher. At 90%, about 130% higher, more than double the rest mass. At 99%, about 600%, 7 times the rest mass. At 99.9%, more than 21 times the rest mass. A heavier object requires more force to accelerate further. More force requires more energy. More energy contributes more mass. More mass requires more energy. Still, the cycle compounds without exit. The energy required to reach any given fraction of light speed equals the rest mass energy times the Lorentz factor minus 1. As the Lorentz factor approaches infinity, the required energy approaches infinity. To reach exactly light speed, you would need infinite energy. Not a large amount. Not a number we can't currently produce, but might someday. Infinite. Without limit. The universe does not provide infinite energy. This is why mass cannot reach the speed of light. not because the engines aren't powerful enough yet. Because the mathematics of space-time, verified to extraordinary precision for over a century, prohibits it structurally. The barrier is not a wall to be broken. It is an asymptote. You can approach it forever. You cannot reach it. Now hold all of that in mind. Because even before you reach light speed, even on the way toward it, the universe begins a cascade of physical processes that no ship, no crew, no technology we can imagine has any answer to. And it starts with something so basic it's easy to underestimate. Space between stars is not empty. It looks empty from Earth. The night sky appears to be darkness with scattered points of light, and the distances between those points seem like pure void. But they are not void. The interstellar medium is the name physicists give to the material filling the space between stars. It contains gas, dust, charged particles, and radiation in quantities that are individually tiny but collectively devastating at the right velocities. The average density of the interstellar medium in the plane of the Milky Way is roughly 1 hydrogen atom per cubic centimeter. In some regions near molecular clouds and stellar nurseries, the density is thousands or millions of times higher. In the hot, rarefied bubbles carved by supernova shock waves, it drops to nearly nothing. But, for a typical path between nearby stars, 1 atom per cubic centimeter is a reasonable working estimate. There is also helium, making up about 8 to 10% of the gas by number. Heavier elements in traces. Dust grains, ranging from large complex molecules to solid particles, roughly a fraction of a micron across. Free electrons and ions from the effects of stellar radiation and cosmic ray interactions. And electromagnetic radiation at every wavelength. At the velocities humans have ever traveled, none of this registers as a meaningful obstacle. A spacecraft, moving at a few tens of miles per second, sweeps through a negligible volume of interstellar space per second, and each atom it encounters imparts essentially no energy to the hull. As velocity climbs toward relativistic values, everything changes. At 10% of light speed, a ship with a frontal cross-section of 100 square meters sweeps through approximately 3 billion cubic meters of space per second. At 1 hydrogen atom per cubic centimeter, that is roughly 3 quadrillion hydrogen atoms per second striking the front of the ship. 3 quadrillion. Every second. Each hydrogen atom striking the front of a ship at 10% of light speed carries kinetic energy of roughly 7.5 times 10 to the negative 13 joules in the ship's reference frame. Per atom, that is a tiny number. Multiply by 3 quadrillion atoms per second per square meter of frontal area, and the deposited power becomes significant. Not immediately lethal at 10% of light speed, but significant enough to erode materials over time, to deposit heat in the leading surfaces, to produce secondary radiation that penetrates further into the ship. Push to 50% of light speed, and the arithmetic becomes brutal. The rate of particle encounters scales linearly with speed. The kinetic energy per encounter scales with the square of speed. The total power deposited in the hull scales with the cube of speed. At 90% of light speed, those hydrogen atoms are not a nuisance. In the ship's reference frame, they are approaching at 90% of light speed. They are cosmic rays. High-energy protons, slamming into the leading face of the hull with energies that ionize material, produce secondary radiation, and physically remove atoms from the surface. This process is called sputtering. It is well understood from both experimental physics and from decades of studying how spacecraft surfaces degrade in Earth orbit, where cosmic ray and solar wind particle fluxes at far lower energies still measurably erode surfaces over years. At relativistic speeds, sputtering becomes catastrophic erosion. The leading face of the hull would be continuously removed, atom by atom and cluster by cluster, at a rate that no replenishment mechanism could match. There is no alloy, no ceramic, no composite material that has ever been tested or theorized that survives indefinite exposure to this flux at relativistic velocities. The engineering problem is not finding a stronger material. It is confronting a process that consumes any material by the laws of physics that govern particle-matter interactions. The dust grains make the problem categorically worse. Interstellar dust particles are rare by number compared to atoms. But at relativistic speeds, even a single encounter is a catastrophic event. A typical interstellar dust grain is a fraction of a micron across. Its mass is roughly 10 to the negative 18 kilograms, or 1 femtogram. At 10% of light speed, that grain carries kinetic energy of roughly 4.5 times 10 to the negative 4 joules when it strikes the hull. Less than half a millijoule. Delivered in an impact area measured in square microns, the local energy density is enormous. The grain vaporizes. The surrounding hull material vaporizes. A tiny crater forms. The encounter produces a brief burst of plasma and secondary radiation. At 10% of light speed, the consequences of individual grain impacts are manageable if they are infrequent enough. The diffuse interstellar medium contains roughly 1 dust grain per several hundred billion cubic meters in typical regions between stars. At 10% of light speed, with a 100 square meter frontal cross-section, the ship encounters 1 grain every 100 seconds or so, on average, roughly once every 2 minutes. A tiny explosion on the leading face every 2 minutes. Over years of travel, manageable perhaps if the hull is thick enough, but pushed to 90% of light speed. The same grain carries kinetic energy of roughly 0.1 joules at impact. That sounds small. Delivered at a grain-sized impact point measuring in square microns, the local energy density at 90% of light speed is still enough to vaporize material and produce a burst of plasma and secondary radiation. And the rate of encounters is 9 times higher than at 10% of light speed. A small explosion on the hull every 12 to 15 seconds on average. Over months. Over years. The cumulative damage is not an engineering challenge to be managed with thicker shielding. It is a continuous process of destruction with no steady state. Whatever mass is added to the leading face, as shielding is removed, grain by grain, at a rate that scales with exactly the velocity squared. The faster you go, the faster the destruction. And there is no velocity at which the process stops. The electromagnetic radiation environment adds a third category of assault, and this one operates independently of any particles in space. Even if you could strip every atom and dust grain from the path between stars, the photons would remain. The universe is filled with electromagnetic radiation. From every direction, at all times, photons are arriving. Visible light from nearby and distant stars. Infrared from warm dust clouds and stellar remnants. Radio waves from pulsars, hydrogen clouds, and interacting star systems. X-rays from stellar coronae, hot gas in galaxy clusters, and compact objects. gamma rays from neutron star magnetospheres, supernova remnants, and matter falling into black holes. And underlying all of it, the cosmic microwave background. The cosmic microwave background is the remnant glow from the early universe. In the first few 100,000 years after the Big Bang, the universe was hot enough that electrons and protons were separate. It was opaque. Photons could not travel freely. Then, as the universe expanded and cooled to a few thousand kelvins, electrons combined with protons to form neutral hydrogen. The universe became transparent. The photons that had been bouncing around in the opaque plasma were suddenly free to travel. They have been traveling ever since. As the universe expanded, those photons were stretched by the expansion. Their wavelengths grew longer. Their energies dropped. What started as the glow of a hot plasma, temperature in the thousands of kelvins, is now a whisper of microwave radiation at a temperature of about 2.7 kelvins. The peak wavelength is about 1.9 millimeters. Deep microwave. The photon energies are tiny, roughly 6 times 10 to the negative 4 electron volts per photon. At rest relative to this background, or moving at ordinary velocities, the cosmic microwave background is harmless. It took dedicated, sensitive instruments to detect it at all. It is the quietest, most pervasive radiation field in the universe. It is also completely inescapable. And, at relativistic speeds, it becomes something else entirely. A ship moving toward a source of electromagnetic radiation experiences those photons. Doppler shifted to higher frequencies. Just as a siren sounds higher pitched as a vehicle approaches you, photons coming from directly ahead appear more energetic to a moving observer. The shift in frequency, and therefore in energy, is given by the relativistic Doppler formula. For photons arriving from directly ahead, the energy shift factor equals the square root of the quantity 1 plus v over c divided by 1 minus v over c. At 10% of light speed, this factor is about 1.1. Cosmic microwave background photons from directly ahead appear 10% more energetic. Still in the microwave range. Still harmless. At 50% of light speed, the shift factor is about 1.73. Those microwave photons now appear as infrared radiation. Still not dangerous. At 90% of light speed, the shift factor from directly ahead is about 4.4. The cosmic microwave background photons arriving from ahead now appear as visible light and near ultraviolet. At 99%, the shift factor is about 14. Those photons are now in the ultraviolet to soft X-ray range. At 99.9% of light speed, the shift factor is about 44. The cosmic microwave background photons arriving from directly ahead are now hard X-rays. The gentlest radiation field in the universe has been transformed by the ship's velocity alone into an X-ray source aimed at the front of the ship. And there is a second effect stacked on top of this. The flux of photons arriving from ahead is also enhanced. Not only does each photon carry more energy, but more photons arrive per second from the forward hemisphere. The ship is moving into the radiation field. The total forward radiation flux scales as the Lorentz factor squared. At 99% of light speed, the forward radiation flux is roughly 50 times more intense than at rest, and each photon carries about 14 times more energy. The combined radiation power arriving at the leading face of the ship is roughly 700 times higher than what a stationary object in the same location would receive. 700 times the X-ray dosage. With no practical shielding that stops high-energy X-rays and doesn't simultaneously add so much mass that the energy requirements to accelerate become impossibly higher. This is the trap. Every solution to one problem makes another worse. Thicker shielding stops more radiation but adds mass. More mass requires more energy to accelerate. More energy means more relativistic mass increase. More relativistic mass requires more energy still. The problems are coupled. Pulling on any one thread tightens the knot. The people inside the ship are not insulated from any of this. Even in the hypothetical scenario where the hull is somehow indestructible and all external radiation is perfectly blocked, the crew is still being destroyed from within by the same physics that makes extended deep space travel hostile to all biological life. The human body evolved on Earth, calibrated to a specific environment. One standard gravity. A nitrogen-oxygen atmosphere at a specific pressure. An electromagnetic radiation environment filtered by a thick atmosphere and a planetary magnetic field. A microbiome, a set of social relationships, a sleep cycle tied to a 24-hour rotation. The body is not a general-purpose machine that can adapt to any environment. It is a highly specialized system, optimized for exactly the conditions in which it developed. Remove those conditions, and the body adapts. But the adaptation is not always beneficial. Begin with gravity. In a spacecraft under sustained thrust at 1 gravity, the crew feels a normal weight. That's good. But between acceleration and deceleration phases, during cruise, the ship is coasting. No net force. No simulated gravity unless the ship rotates. Even with rotation to simulate gravity, the rotating section has a gradient. The effective gravity at the center of rotation is 0. The effective gravity at the rim is what the rotation provides. Any crew member moving between areas experiences this gradient continuously. And rotation has its own physiological challenges. The vestibular system, the inner ear's balance and motion detection apparatus, is exquisitely sensitive to rotation. The Coriolis effect, which appears when a body moves within a rotating reference frame, produces what feels like a force deflecting motion sideways. At the rotation rates needed to generate meaningful simulated gravity in a realistically sized spacecraft, the Coriolis effect is noticeable and disorienting. The minimum radius at which most people can tolerate rotation without severe motion sickness is thought to be around 150 to 200 meters. A spacecraft with that kind of rotating section is an enormous structure. Enormous structures are enormously expensive to build and launch. And they add to the mass problem. Extended weightlessness, when it occurs, causes changes that compound over time. Bone density falls at roughly 1 to 2% per month in the most affected areas, the spine and lower limbs, in crew members aboard the International Space Station. Even with dedicated exercise regimens designed to slow this loss, the degradation continues. After a year in weightlessness, the bone loss in some areas approaches 15 to 20% of original density. The fracture risk on return to a gravity environment is substantially elevated. The cardiovascular system restructures. The heart remodels toward a more spherical shape in weightlessness, and cardiac output during exercise decreases. The blood volume redistribution toward the upper body triggers compensatory mechanisms that reduce overall blood volume. The body interprets the fluid shift as excess fluid and eliminates it. When gravity is restored, the reduced blood volume means the heart must work harder than before to pump blood through the full body. Some cardiovascular changes appear to persist even after extended rehabilitation. The eyes change. Fluid pressure in the skull increases in weightlessness because fluid that normally pools in the lower body in gravity now accumulates in the upper body and head. This increased intracranial pressure flattens the back of the eye and causes changes to the optic disc. The condition is now called spaceflight-associated neuroocular syndrome, and it is one of the most worrying long-term health effects of spaceflight. Vision changes, documented in returning astronauts, include farsightedness that was not present before the mission. Structural changes visible on imaging. Some alterations that do not fully reverse even after years back on Earth. The mechanism is not entirely understood, but the effect is real, documented, and occurs in a substantial fraction of crew members on long-duration missions. After years aboard a relativistic spacecraft, these effects would be far more advanced than anything observed in 6-month ISS rotations. The crew, arriving at a destination star system, would be doing so with compromised bone density, altered cardiovascular function, and potentially degraded vision. They would need months or years of rehabilitation before being physically capable of the surface exploration that would presumably be the point of the mission. The radiation environment in deep space, independent of any relativistic blue shifting of background photons, is already a serious problem. Galactic cosmic rays are atomic nuclei, mostly protons, but also helium nuclei and heavier elements up to and including iron, accelerated to relativistic velocities by the most violent events in the galaxy. They originate in supernova shocks, neutron star magnetospheres, pulsar wind nebulae, and the acceleration regions near active galactic nuclei. Once accelerated, they travel through the galaxy for millions to hundreds of millions of years, scattered by magnetic fields, losing energy gradually through interactions with photons and other particles. When they finally reach our solar system, Earth's magnetic field deflects the lower energy ones. Earth's atmosphere absorbs the rest, producing cascades of secondary particles that spread through the air before losing energy entirely. At the surface, the galactic cosmic ray flux is a small fraction of what exists in open space. In Earth orbit, still within the magnetosphere, astronauts receive radiation doses roughly 100 to 200 times higher than people on the ground. A 6-month stint on the International Space Station causes a measurable increase in lifetime cancer risk. Beyond Earth's magnetic field, in deep space, the galactic cosmic ray flux is higher. A hypothetical crewed mission to Mars, lasting somewhere between 18 months and 3 years, it would expose crew members to radiation doses that NASA estimates increase lifetime cancer risk by roughly 5%. That's considered near the acceptable limit for a mission of exceptional scientific value. A journey to even the nearest star, lasting years of subjective crew time in deep space, accumulates radiation exposure that exceeds any established safety standard by factors of 10 to 100. The biological damage from galactic cosmic rays is also qualitatively different from ordinary ionizing radiation. A medical X-ray spreads a dose of relatively low-energy photons through tissue. Cells are damaged individually, scattered across the irradiated volume. The body's DNA repair mechanisms can handle this kind of scattered, low-density damage reasonably well. a galactic cosmic ray, particularly a heavy nucleus, like iron, moving at a substantial fraction of light speed, passes through biological tissue differently. It leaves a dense track of ionization damage along its entire path. The nuclei it passes by are ionized and physically disrupted. Molecular bonds are broken. DNA strands are shattered and cross-linked in complex patterns. The damage is not scattered. It is concentrated along a track that may be millimeters to centimeters long, depending on the particle energy and tissue type. Secondary particles, called delta rays, fan out from the primary track, extending the damage zone outward. A single ion cosmic ray can pass through dozens of cells along its track and affect neighboring cells through delta ray ionization. The body's DNA repair machinery, evolved to handle the scattered damage of background radiation, struggles with this kind of dense, structurally complex damage. Misrepair creates chromosomal abnormalities. Failed repair leaves double-strand breaks. Both outcomes increase cancer risk and can lead to cell death. In the brain and nervous system, where mature neurons do not regenerate, cell death is permanent. The neurological impact of extended galactic cosmic ray exposure in deep space was not just theoretical concern, until studies in the early 21st century began quantifying it. Animal studies, primarily using mice exposed to accelerated heavy ion beams, simulating the galactic cosmic ray environment, showed consistent results. Neuroinflammation. Reduced rates of neurogenesis in brain regions that normally generate new neurons, including the hippocampus. Impaired performance on cognitive tests, measuring learning, memory, and problem-solving. Altered anxiety-related behavior. Changes to synaptic structure that persisted for the lifetime of the animals studied. These effects appeared at radiation doses consistent with what a crew would receive on multi-year interstellar journeys. A crew member completing a decade-long voyage to a nearby star would arrive with measurable cognitive impairment, elevated cancer risk from both galactic cosmic rays and any blue-shifted background radiation that penetrated the shielding, advanced bone density loss, and cardiovascular changes of uncertain severity. They would not arrive as the healthy, capable adults who departed. They would arrive as people who had been through something the human body was not designed to survive. The energy problem is perhaps the most fundamental because it underlies every other challenge. To accelerate a spacecraft to a significant fraction of light speed requires enormous energy. The relativistic kinetic energy of an object equals the rest mass energy times the Lorentz factor -1. In symbols, kinetic energy equals mc² times the quantity gamma -1. At non-relativistic speeds, this reduces to the familiar 1/2 mv². At relativistic speeds, the Lorentz factor correction makes the required energy far greater than the classical estimate. Consider a spacecraft with a dry mass of 1 million kilograms, 1,000 tons. This is not large by the standards of anything that needs to keep humans alive for years or decades. The International Space Station masses about 420 tons and cannot keep people alive indefinitely without resupply. A real, crude interstellar vehicle would need life support capable of recycling air and water for years, food production or storage for decades, radiation shielding measured in tons, medical facilities, spare parts for every critical system, structural integrity across the entire ship, and the propulsion system itself. 1 million kilograms is an optimistic lower bound. The rest, mass energy of 1 million kilograms, is 9 times 10 to the 22nd joules. That is the total energy output of the Sun over approximately 4 minutes. To accelerate this spacecraft to 10% of light speed, the required kinetic energy is roughly 4.5 times 10 to the 20th joules. About 30 times the annual electricity consumption of the entire United States. To 50% of light speed, about 1.4 times 10 to the 22nd joules. To 90%, about 1.2 times 10 to the 23rd joules. And to 99% of light speed, about 5.5 times 10 to the 23rd joules. That last number is about 6 times the rest mass energy of the ship itself. But the propellant that produces this energy must also be accelerated. The propellant has mass. That mass requires energy to accelerate, which requires more propellant. The rocket equation, formulated in its classical form by Konstantin Tsiolkovsky in 1903 and extended to relativistic velocities by subsequent physicists, describes this compounding relationship. For a perfectly efficient antimatter drive, the theoretical maximum efficiency for a conventional propulsion system, the mass ratio required to reach 90% of light speed is about 5 to 1. 5 kilograms of initial vehicle, including fuel, for every 1 kilogram that reaches the target speed. 4/5 of the initial mass is propellant. To also decelerate at the destination, you need another factor of 5. The combined mass ratio for a one-way trip that includes stopping is about 25 to 1. For every kilogram of spacecraft stopped at the destination, you need 24 kilograms of propellant at departure. For our 1 million kilogram spacecraft, that's 24 million kilograms of propellant. For a perfectly efficient antimatter drive, that propellant is equal masses of matter and antimatter, 12 million kilograms each. 12 million kilograms of antihydrogen. Current global production of antihydrogen at the world's most advanced particle physics facilities is roughly 10 nanograms per year. A nanogram is a billionth of a gram. The gap between what we can produce and what we would need is roughly 21 orders of magnitude. That is 10 to the 21st. 1 sextillion. This gap is not an engineering challenge. It is not the kind of problem that decades of incremental progress can close. It is a difference so vast that it puts interstellar travel by conventional antimatter rocket beyond the reach of anything we can reasonably project in any timeline. And antimatter is the theoretical maximum for a propulsion system that carries its fuel. Every other proposed technology, fusion rockets, fission drives, nuclear pulse propulsion, falls below this theoretical limit. They require more propellant, not less. The mass ratio problem compounds in their favor even more unfavorably. There is a further complication that rarely appears in popular discussions of light-speed travel, and it concerns the behavior of the quantum vacuum at relativistic velocities. The quantum vacuum is not empty. Classical physics says a perfect vacuum contains nothing. Quantum mechanics says otherwise. Even empty space is filled with quantum fluctuations, virtual particle pairs that spontaneously appear and disappear on timescales so brief they are consistent with the Heisenberg uncertainty principle. These virtual particles do not persist. They appear, separate briefly, and annihilate each other in times shorter than any direct measurement can resolve. From the perspective of an observer at rest, the vacuum looks calm. The virtual particles cancel out. No net energy or momentum is transferred to any measurement device, and the vacuum appears truly empty. But from the perspective of an accelerating observer, something changes. William Unruh, a Canadian physicist, showed in 1976 that an accelerating observer experiences a thermal bath of real particles where a non-accelerating observer sees vacuum. This is now called the Unruh effect. The temperature of this thermal bath, the Unruh temperature, is proportional to the acceleration. At ordinary accelerations, the Unruh temperature is immeasurably small. At one standard gravity of acceleration, the Unruh temperature is approximately 4 times 10 to the negative 20 kelvins. The coldest temperatures achieved in any laboratory are about 10 to the negative 10 kelvins. The Unruh temperature at normal accelerations is more than 2 billion times colder than the coldest thing humans have ever made. Completely unmeasurable and irrelevant at everyday accelerations. But the Unruh effect becomes relevant at extreme accelerations. The temperature scales linearly with acceleration. 10,000 times the acceleration of gravity produces an Unruh temperature 10,000 times higher. Still tiny in absolute terms, but the principle is real and has been experimentally supported through analogous effects in other physical systems. For a spacecraft attempting to reach relativistic speeds quickly, the required accelerations during certain phases of the journey could approach regimes where the Unruh effect becomes physically significant. More immediately, the same mathematical structure that produces the Unruh effect also predicts that horizons generate radiation. Any boundary that separates regions of space-time in ways analogous to a black hole horizon should, by the same physics that produces Hawking radiation from black holes, generate a thermal radiation field. A ship moving at high velocity through space creates a kind of Rindler horizon, a boundary behind the ship beyond which accelerated away signals cannot catch up. The physics of quantum fields in the vicinity of this structure is not fully resolved for relativistic spacecraft, but the direction the mathematics points is not encouraging. Hawking radiation from actual black holes is faint because black holes are large, and radiation temperature scales inversely with the horizon radius. But structures with smaller effective horizon radii are hotter. A sufficiently relativistic spacecraft creates a causal structure with horizon-like features at much smaller scales than astrophysical black holes. The quantum radiation effects associated with those features are, in principle, more intense. The exact magnitudes are not calculable with current theory, because the relevant questions about quantum fields in extreme spacetimes require a complete theory of quantum gravity, which does not yet exist. But the existence of these effects is not speculative. They follow from the same physical framework that has been verified in other contexts. The universe generates radiation wherever causal structure changes. A relativistic spacecraft creates causal structure. What it generates as a result is an open question. The fact that it generates something is not. The time dilation that shortens the crew's experience of the journey also creates an asymmetry that is easy to overlook until its full implications sink in. A crew, traveling at 99% of light speed toward a star, 40 light-years away, and then returning, arrives back at Earth having experienced about 11 years of travel. Earth has experienced 80 years. A crew member departing at age 30 returns at biological age 41. 80 years have passed on Earth. The world they left is unrecognizable. Everyone they said goodbye to at their departure is either very elderly or gone. Their children, if they had children, are as old as they are or older. Their professional field has evolved through 80 years of additional progress. Their cultural context has been replaced by 3 or 4 generations of change. The civilization that funded the mission and waited for the results is not the civilization that exists now. This is not a flaw in the mission design. It is a feature of the physics. You cannot turn off time dilation. You cannot opt out of its social consequences. Every year of subjective time saved by the traveler is a year of real time that passed without them on Earth. The faster you go, the more disconnected from your departure point you become. At some extreme velocity, where the crew experiences only a year of travel, decades or centuries may pass outside. They would return to a world with no living connection to the one they left. No one who remembers them as young. No cultural reference point they recognize. No institution they once belonged to that still exists in the same form. This is not a human problem to be solved by better psychological preparation or improved communication technology. It is the physical geometry of relativistic spacetime applied to human lives. The communicational isolation makes it worse. Radio signals travel at the speed of light, but a ship moving away at 90% of light speed means any message sent from Earth must close a widening gap at only 10% of light speed. A message gains on the ship slowly. By the time the ship reaches 1 light year out, a message sent then takes 10 years to catch up. After the ship travels several light years, exchanging a question and answer takes decades. Real-time coordination is impossible within weeks of departure. Real-time conversation is gone within months. What remains is the transmission of information across a one-way time gap that grows throughout the mission. The crew sends updates about conditions aboard the ship. Earth responds with technical guidance or personal messages. Both parties are corresponding with a version of the other that existed years ago. The ship and its home planet become, over the course of a relativistic journey, effectively separate civilizations communicating across a time delay that makes shared decision-making impossible. Every significant choice made en route must be made autonomously by the crew. Every emergency must be handled with what is on board. There is no help coming. There is no expert available for consultation whose answer will arrive in time to matter. The crew is, in every practical sense, alone. The social and psychological dimensions of this isolation are not soft considerations. They are operational necessities that any realistic assessment must account for. Human beings evolved as social animals in small groups. Our cognitive architecture, our emotional needs, our mental health, all of it was shaped by a context of close social bonds, varied environments, regular change, and the possibility of leaving situations that become intolerable. None of those features exist on a relativistic spacecraft. The same small group of people, the same enclosed environment, the same routines imposed by the requirements of keeping the ship functioning. No possibility of leaving, of taking a vacation, of escaping a conflict, of seeking new company. For years. For decades. Research on isolated, confined environments. From Antarctic research stations to submarine crews to long-duration spaceflight simulations, consistently shows that psychological health deteriorates over time in ways that are difficult to prevent with known interventions. Interpersonal conflicts escalate. Leadership challenges emerge. Motivation declines. sleep disrupts. Cognitive performance degrades even without the cosmic ray contribution to neurological damage. Depression and anxiety are common. In extreme cases, psychotic episodes have occurred in isolated environments. In a spacecraft years from any possible rescue, a psychological crisis among one or more crew members is not just a personal tragedy. It is an operational risk to the entire mission and everyone aboard. The person experiencing the crisis cannot be helped by specialists. They cannot be removed from the situation. They must be managed by the people around them, who are themselves under the same isolation stress, with whatever medical and pharmaceutical resources were loaded at departure. The social dynamics among a small group of people sealed in an enclosed environment for years are poorly understood because humans have never done anything exactly like this before. Spaceflight analogues give us information, but none matches the true scale of what a relativistic interstellar mission would impose. The closest analogues, long-duration Antarctic expeditions, the biosphere, 2 experiment of the early 1990s, various isolation studies, all showed that the social and psychological challenges were at least as operationally significant as the technical ones. Some ended in serious interpersonal conflict, team breakdown, or individual psychological crisis. None lasted more than 2 years. A crewed mission to the nearest star, even at speeds we cannot currently achieve, would last years of crew subjective time at minimum, and likely much longer. The social architecture of the crew, the leadership structure, the conflict resolution mechanisms, the psychological support systems are not afterthoughts. They may be the decisive factor in mission success or failure. Underlying all of these specific problems is a more general issue that the dream of light-speed travel tends to obscure. The reason the speed of light is the maximum speed for massive objects is not arbitrary. It is not a coincidence. It is not a rule that could have been different. The speed of light is the maximum propagation speed for causal influences in a universe structured the way ours is. Causality, the principle that causes precede their effects, is not just a convenient assumption. It is the operational basis for the entire framework of physics. Chemistry works because reactions happen in a specific order. Biology works because molecular processes occur in causal sequences. Minds work because information is integrated and responded to across time in a consistent direction. If faster-than-light travel were possible, then according to the mathematics of special relativity, observers in different states of motion would disagree about the order of events. What one observer sees as a message sent before it was received, another observer would see as a message received before it was sent. What one sees as a cause, another would see as an effect. The consistent time ordering that makes physics coherent, that makes chemistry predictable, that makes life possible, breaks down. This is not a hypothetical concern. The mathematics is explicit and has been verified. The Lorentz transformations, derived directly from the postulates of special relativity, show that if faster-than-light communication is possible, then causal paradoxes are possible. Messages can be sent back in time. Effects can precede causes. The framework loses internal consistency. Physics resolves this by making faster-than-light travel for massive objects impossible, not by decree, but by the structure of the equations. Every solution to Einstein's field equations that appears to allow faster-than-light travel, warp drives, traversable wormholes, tachyonic motion, turns out, on closer examination, to require exotic matter with properties that may not exist to generate lethal radiation effects, or to produce the very causal paradoxes that physics works to prevent. The universe is not being arbitrary, it is being consistent. And consistency, it turns out, requires that nothing with mass travels at the speed of light. That particular rule, annoying as it is for the dream of interstellar travel, is a consequence of the universe being the kind of place where chemistry and biology and minds are possible at all. There are proposals for getting around these problems, and they deserve honest examination. The Bussard ramjet, proposed by Robert Bussard in 1960, imagined a spacecraft with a vast electromagnetic scoop ahead of it, hundreds of miles across. The scoop would collect interstellar hydrogen as fuel, funnel it into a fusion reactor, and burn it for thrust. No need to carry propellant. The interstellar medium itself becomes the fuel supply. The faster you go, the more hydrogen you collect per second, potentially allowing continuous acceleration without an onboard fuel limit. It's a beautiful concept. The physics is not supportive. Proton-proton fusion, the fusion of ordinary hydrogen nuclei, is extraordinarily difficult to sustain in a compact reactor. The Sun achieves it at the scale of the entire solar mass, under pressures and temperatures achievable only in stellar interiors. The rate of proton-proton fusion in even the Sun's core is surprisingly slow per unit volume. A paper by T.A. Heppenheimer in 1978 found that the energy losses from compressing protons to fusion densities in the form of Bremsstrahlung radiation would exceed the power produced by fusion by a factor of roughly 1 billion. You would be slowing yourself down. Later proposals modified the design to use different fusion reactions, or to use the scoop for braking at the destination rather than for propulsion throughout. These modifications reduce the elegance of the original concept and introduce their own problems without solving the fundamental issues of the journey. The laser light sail is another approach with genuine partial merit. A laser array, based on Earth or in orbit, fires a sustained beam at a reflective sail attached to the spacecraft. Light carries momentum. The sail reflects the beam and is pushed forward. No propellant required aboard the ship. The Breakthrough Starshot initiative, funded by the late physicist Stephen Hawking, among others, proposed using this approach to push gram-scale probes to 20% of light speed. The physics works for tiny probes. For a crewed spacecraft, the scaling is ruinous. A sail large enough to push a crewed ship requires laser array powers that tax even the most optimistic projections of future energy infrastructure. The aiming precision required to keep the laser on the sail across light minutes or light hours of distance is unprecedented. And at the destination, there are no lasers. The ship cannot stop. It flashes through at full speed, takes measurements in the hours it has, and continues into the darkness. The crew, if there were one, would arrive at the target system without the ability to stop, without the ability to orbit, without any prospect of return. That is not exploration in any meaningful sense. The Alcubierre warp drive, derived from Einstein's field equations in 1994 by physicist Miguel Alcubierre, describes a space-time geometry in which a bubble of flat space-time moves through the universe faster than light. The object inside the bubble doesn't move through space. The space itself moves. It's mathematically valid as a solution to Einstein's equations. The problems are severe. The original design requires exotic matter with negative energy density. Negative energy density is not known to exist in the universe in the required quantities. Small quantum effects, like the Casimir effect between closely spaced metal plates, produce tiny amounts of negative energy. But scaling these effects to the quantities required for a macroscopic warp bubble appears physically impossible under current theory. Superluminal variants of the warp bubble also generate Hawking radiation at the leading edge of the bubble, in a process formally analogous to black hole evaporation. Calculations suggest this radiation would be lethal to any crew inside the bubble. The radiation is generated between the crew and the front wall of the bubble. You cannot shield against it by putting material between the crew and the leading edge, because the shielding would disrupt the bubble geometry and collapse the drive. Recent work has shown that warp drives without exotic matter are theoretically possible for subluminal designs. But subluminal means slower than light. A subluminal warp drive is not a solution to the interstellar distance problem, even if it offers other advantages, like reducing crew-experienced acceleration forces. Every route toward faster-than-light travel runs into its own wall. The walls look different from different angles. They are all made of the same material, the structure of space-time itself. The honest picture, stripped of optimistic framing, is this: the speed of light cannot be reached by any object with mass. Approaching it creates an environment of particle bombardment, blue-shifted radiation, and energetic erosion that destroys any ship and ends any crew faster than they can arrive anywhere. The energy requirements for relativistic travel are so far beyond any achievable propulsion technology that no engineering roadmap currently leads there. The biological effects of extended deep space travel, even without the relativistic effects, are severe and only partially mitigated by current and foreseeable technology. The time dilation that allows subjectively shorter journeys simultaneously severs travelers permanently from the social context that makes life meaningful. The dream, in its popular form, of jumping aboard a starship and arriving at another world in a few weeks is not waiting for better technology. It is in contradiction with the structure of the universe. And yet, the stars remain. There are hundreds of billions of them in our galaxy alone. There may be planets around most of them. There may be chemistry on some of those planets. There may be complexity on some of those planets. There may be minds. The universe is almost certainly not empty of things worth knowing about. We just cannot reach them at light speed. What we can do, in principle, is reach them slowly. At 10% of light speed, a goal within the theoretical reach of advanced fusion propulsion, though still far beyond our current capability. The nearest star is a 43-year journey, a human career, stretched. Enough for a dedicated crew who departed young. The challenges are real and immense. The radiation, the physical deterioration, the isolation, the social dynamics, the engineering reliability requirements over multi-decade timescales. None of these are solved. But none of them are forbidden by the structure of space-time. They are engineering problems. The hardest engineering problems in the history of the species, but not impossible ones. The light-speed barrier is the one genuinely closed door. The door marked infinite energy required, hull eroded by particle flux at relativistic speeds, crew irradiated by blue-shifted background radiation, propellant requirements 20 orders of magnitude beyond any production capability, causality itself threatened by the attempt. Everything else is a door not yet opened. Hard. forbidding, not yet reachable, but not locked by the laws of physics. What the full, honest reckoning with light-speed travel teaches us is something about the relationship between human ambition and physical reality. We have a long history of declaring things impossible and then achieving them. Flight was impossible until it wasn't. Nuclear energy was impossible until it wasn't. The vaccines and medicines that ended diseases that once carved through entire civilizations were impossible until they weren't. The pattern is real. Our categories of impossible and possible shift as understanding deepens. But there is an important difference between the impossibilities that gave way and the one we're discussing now. The impossibility of heavier-than-air flight was a failure of engineering intuition, not a fundamental structural feature of the universe. No physical law prohibited it. The impossibility of controlled nuclear fission was a failure of materials, science, and theoretical understanding, not a fundamental structural feature of the universe. No law prohibited it. The impossibility of light-speed travel for massive objects is different. It is not a failure of engineering or understanding. It is a derived consequence of the most precisely tested physical framework in history. Special relativity, confirmed to 1 part in 10 to the 17th by atomic clocks and GPS systems. The constancy of the speed of light, verified to better than 1 part in 10 to the 22nd in all directions. The relativistic mass increase, directly observed in every particle accelerator on Earth. These are not approximations, awaiting correction. They are the most precisely measured relationships in the history of science. Overturning them would not be a revision of physics. It would require a revolution so complete that every experiment ever done would need reinterpretation. That cannot be ruled out with absolute certainty. Science has produced revolutions before, but the sheer weight of confirmed evidence makes it the least likely scenario we can rationally entertain. The more productive approach is to take special relativity seriously, accept what it says about light-speed travel, and build from there. What it says is, not at light speed. What it does not say is, not ever, not at any speed, not to any star. Not at light speed is a real constraint. The others are targets. The next serious step toward the stars will probably not be a human crew in a relativistic spacecraft. It will probably be an unmanned probe, sent at a fraction of a percent of light speed, using the best propulsion technology we can build at that time, taking centuries to reach the nearest stars, sending back data that arrives years or decades after transmission. We will not be there to see it in person. We will be the civilization that built the thing and trusted the physics and waited. After that, there may be small, unmanned probes at higher velocities. Then larger ones. Then designs with increasingly capable on-board autonomy. The history of how humanity has extended its reach from the first stone tools to the surface of the moon suggests that the process is not sudden. It is not a single breakthrough. It is a long sequence of steps, each enabled by the previous ones, each opening new problems that the next step must solve. The journey to the stars is that process, extended across civilizational timescales. It does not require finding a way around the speed of light. It requires everything else to go right first. The propulsion, the radiation protection, the life support, the social architecture, the sheer sustained commitment of a civilization to a goal that will not pay off within any individual human lifetime. All of that is harder than it sounds. None of it is prohibited by physics. And that is the real conclusion of the story. Not that the stars are unreachable, that they are reachable, but not quickly. Not at the speed of light, which would destroy you before you arrived, but at the speeds that are actually available, which will take much longer and cost much more. The universe did not make this easy, but it did not make it impossible. The difference matters. The problem of stopping is as severe as the problem of getting up to speed, and it is routinely ignored in popular discussions of interstellar travel. Getting to relativistic speed requires enormous energy expenditure over an extended period. But physics is symmetric. Deceleration requires the same energy as acceleration. The kinetic energy you added on the way up must be removed on the way down. Every unit of momentum you gained through thrust must be shed through thrust before you can stop at the destination. This is not a clever engineering puzzle with an elegant solution. It is a fundamental consequence of how kinetic energy works. You cannot simply deploy a parachute in the interstellar medium. The density of the medium is far too low to provide meaningful aerodynamic braking at any reasonable hull size. You cannot simply turn off the engines and drift to a stop. There is no friction. An object in space, moving at 90% of light speed, will still be moving at 90% of light speed a million years from now, unless something acts on it. The only practical option is thrust. Burn propellant in the opposite direction. Slow down the same way you sped up. This means carrying the deceleration fuel along for the entire journey. The fuel needed to stop at the destination must be accelerated from Earth, along with everything else. The fuel needed to accelerate that deceleration fuel must also be brought. The compounding of the rocket equation applies in both directions. For a perfectly efficient antimatter drive, as noted earlier, the combined mass ratio for a one-way trip that includes stopping at the destination is roughly 25:1. But now, consider a round trip. To return from the destination, the crew needs fuel for the departure from the destination system, and fuel for the deceleration back at Earth. This is another factor of roughly 25 applied to the mass arriving at the destination. For a round trip at 90% of light speed, the mass ratio from Earth departure to Earth arrival is roughly 25 squared, about 600:1. For every kilogram of crew and equipment that makes the round trip, you need roughly 599 kilograms of propellant. For a crew vehicle with a dry mass of 1 million kilograms, the departure mass is approximately 600 million kilograms. 600,000 tons of antimatter and matter propellant. The quantity of antimatter alone would be several 100,000 tons. The entire global production of antihydrogen across all human civilization, running all current facilities continuously, would produce this amount in roughly 10 to the 23 years. The universe is about 13.8 billion years old. That is about 10 to the 10 years. The production time required exceeds the age of the universe by 13 orders of magnitude. The numbers are not engineering constraints. They are statements about the structure of reality. Consider what the hull of a relativistic spacecraft would actually have to be made of, and why no material that exists satisfies the requirements. At relativistic speeds, the leading face of the hull is not a passive structural element. It is an active collision zone being continuously eroded by hypervelocity particle impacts. The physics of hypervelocity impact is well studied, from research into spacecraft protection meteor crater formation, and ballistic armor science. At impact velocities of a few miles per second, which is the regime of typical orbital debris, a projectile striking a metal plate creates a crater several times its own diameter. The projectile partially vaporizes. A shockwave propagates through the plate. Material is ejected from the impact point. At impact velocities of tens of miles per second, the behavior changes. The impactor and the surrounding material both vaporize explosively. The impact is better described as a localized detonation than a physical collision. At the impact velocities relevant to relativistic spacecraft, where the interstellar medium is approaching at a significant fraction of the speed of light in the ship's reference frame, even individual hydrogen atoms carry enough energy to produce X-ray radiation upon impact. The material response in this regime is not well characterized experimentally because no ground-based facility can accelerate macroscopic objects to a significant fraction of light speed. Theoretical models and extrapolations from available data suggest that no conventional engineering material withstands continuous exposure to this flux. Metals experience a process called radiation damage. Individual atom displacements in the crystal lattice occur when energetic particles pass through, knocking atoms from their equilibrium positions. Enough displacements, and the crystal structure becomes amorphous. Voids form where clusters of displaced atoms accumulate. The mechanical properties degrade. The material becomes brittle. The thermal conductivity changes. The electrical properties change. Ceramics, which have less regular crystal structure than metals, behave somewhat differently under radiation. They can tolerate higher displacement doses before catastrophic failure. But they are brittle to begin with, and any cracking from thermal stress or mechanical loading becomes critical faster than it would in a ductile metal. Carbon fiber composites, which are used extensively in aerospace applications for their high strength-to-weight ratio, are particularly vulnerable to radiation. The carbon-carbon bonds in the polymer matrix are readily broken by energetic particles. The matrix degrades. The load transfer between fibers is impaired. The composite loses both stiffness and strength over time. Diamond, which is the hardest naturally occurring material and has excellent radiation tolerance in some respects, cannot be produced in the shapes and sizes needed for spacecraft structures. Novel materials based on nanotubes, graphene, or other engineered structures at the nanoscale have been studied theoretically and in small quantities in laboratories. Their radiation tolerance under sustained relativistic velocity particle bombardment is unknown because no facility can test them under those conditions. The general principle holds regardless of the specific material. Any material exposed to continuous high-energy particle bombardment will degrade over time. The rate depends on the material and the flux. The direction is universal. There is no known material that is immune to radiation damage under sufficiently intense conditions. A relativistic spacecraft would carry the most intense particle bombardment any human-built structure has ever experienced for the longest continuous period any human-built structure has ever operated. The intersection of those two facts leaves no known candidate material intact at the end of the journey. The navigation problem for a relativistic spacecraft is a puzzle that most discussions of interstellar travel skip, and it is not trivial. Stars are not stationary. The entire galaxy is in motion. Every star, including our own Sun, is orbiting the galactic center at roughly 500,000 miles per hour. Each star orbits at a different speed and in a slightly different direction, depending on its position and the gravitational influences it experiences. From Earth, nearby stars appear to move slowly across the sky over decades. This proper motion, the apparent shift in a star's position against the background of more distant stars, reflects the actual motion of the star through space relative to us. Proxima Centauri, the nearest star, has a proper motion of about 3.85 arc-seconds per year. In absolute terms, it is moving roughly 16 miles per second relative to the Sun. A spacecraft aimed at Proxima Centauri's current position would miss it. The star will have moved. Navigation to a relativistic spacecraft's destination requires predicting where the target star will be when the spacecraft arrives, not where it is when the spacecraft departs. For a journey lasting decades, a star moving at 16 miles per second relative to the ship's reference point will have moved by a substantial distance. The calculation is not trivially simple. The ship is also moving. Both the star and the ship are subject to gravitational influences from other masses. The galactic potential well affects both trajectories. Nearby stars, even ones well off the direct path, exert gravitational tugs over decades of travel. The calculation requires continuous updating throughout the journey. Measurements must be taken regularly to verify that the ship is on the correct trajectory and to make adjustments as needed. But measurement at relativistic speeds has its own complications. The light from stars ahead of the ship is blue-shifted. Stars behind are red-shifted. The visual appearance of the sky, the map the crew would use to navigate, is continuously distorted in ways that depend on the ship's current velocity. A star chart made for Earth observers is not directly applicable. Corrections must be applied. The corrections depend on knowing the ship's velocity to high precision. The ship's velocity is itself measured using Doppler shifts of reference stars. The measurements and corrections are coupled. At 10% of light speed, the Doppler effects are modest, and the navigation corrections, while necessary, are tractable. At higher fractions of light speed, the sky looks increasingly different from Earth-based charts. The stars ahead cluster together in a phenomenon called relativistic aberration. Ahead of the ship, the apparent density of stars is higher than Earth-based observers see. Behind the ship, stars appear spread out. The entire celestial sphere is distorted in ways that must be accounted for in navigation. Maintaining a trajectory toward a star that is moving relative to you, while yourself moving at relativistic speed through a galaxy in motion, while correcting for a sky that looks nothing like the charts you started with, is a navigation problem that exceeds anything in human experience. It requires continuous, accurate measurement, sophisticated computation, and small trajectory corrections using propellant that must be budgeted in advance. Any error in the initial trajectory compounds over the years of the journey. A small deviation in heading at departure becomes a large positional error at arrival. The ship might arrive in the vicinity of the target star system, but miss the specific inner system where any planets and points of interest are located. A course correction from a distance of light weeks from the star requires time and propellant. Time spent approaching at the wrong angle is time that must be corrected. Propellant for corrections is propellant that was carried the entire journey. It is mass that was part of the initial fuel budget. Navigation errors have mass costs. The thermal management challenge for a relativistic spacecraft is equally understated in popular discussions. A ship moving at relativistic speed generates heat through multiple mechanisms that must all be rejected to the external environment. The engines, whatever form they take, produce waste heat. No propulsion system converts fuel into thrust with perfect efficiency. The inefficiency manifests as heat. On Earth, waste heat is rejected to the atmosphere, to water, to the ground. In space, the only mechanism for heat rejection is radiation. Heat can only leave a spacecraft by being radiated away as infrared photons. The rate of heat rejection depends on the temperature of the radiating surface and the surface area. Stefan Boltzmann's law tells us that radiated power scales with temperature to the fourth power and with surface area. To reject large amounts of waste heat, you need either very high temperatures or very large surface areas. Large surface areas mean large mass, which means more fuel required for acceleration. High temperatures mean materials operating near their limits, which means faster degradation and higher risk of failure. For a spacecraft running antimatter engines at the power levels needed for relativistic flight, the waste heat problem is severe. Even a system with 99% efficiency, which is far better than anything achievable today, would produce 1% of engine output as waste heat. At the power levels required for relativistic acceleration of a 1,000,000 kilogram spacecraft, 1% is still an enormous heat load. The radiator panels required to shed this heat without overheating the ship would be enormous. But the radiators would also be exposed to the relativistic particle flux. The same particle bombardment that erodes the leading hull also erodes the radiators. The radiators must face away from the direction of travel as much as possible, but even side-facing surfaces receive scattered radiation. The degradation of radiator surfaces reduces their emissivity over time. Reduced emissivity means reduced heat rejection, which means higher internal temperatures, which means stress on all other systems. The thermal management subsystem and the radiation protection subsystem interact in ways that make the design of either one dependent on the other. The ship is not a collection of independent systems. It is a coupled system in which every component affects every other. Making any single component more robust typically places higher demands on neighboring components. This coupling is why systems engineering for complex spacecraft is enormously difficult, even for relatively simple missions like Mars orbiters. For a relativistic interstellar spacecraft, the number of strongly coupled subsystems and the extremity of the operating environment create a design challenge that has no parallel in existing engineering practice. Beyond all the physical challenges, there is a structural question about what kind of civilization could actually commit to an interstellar mission. An interstellar mission at sublight speeds, even the fastest plausibly achievable, is a project on timescales that exceed any institutional structure in human history. A 43-year journey at 10% of light speed, if that were ever achievable, is still longer than most human careers. The engineers who design the ship will retire before it arrives. The mission controllers who track it will retire. The scientists who defined the mission's scientific goals will retire. The political entities that funded it will have changed governments several times. The cultural values that motivated it may have shifted. The technical context in which the mission was designed will have advanced, perhaps to the point where the mission's original design looks obsolete. All of this has to be accounted for in how the mission is structured. The spacecraft must be designed not just for the 43 years of travel, but for the possibility that the technological and organizational context on Earth will change significantly during that time. Mission control systems that can function across personnel changes of multiple generations. Software and communication protocols that can be updated during the journey to remain compatible with whatever systems Earth is using when the ship arrives. A crew selection and training process that prepares people for a journey they may not live to complete. A legal and institutional framework that maintains responsibility and authority across a journey where no person alive at departure is alive at arrival. These are not technical problems. They are civilizational ones. Human institutions, companies, governments, universities rarely sustain focus on specific goals across decades. The Apollo program, one of the most focused, sustained technical achievements in history, lasted about a decade before political support waned. A mission requiring 43 years of sustained commitment, with no results deliverable for the first 43 years, would test the durability of any institutional structure in ways that have no historical precedent. This is not an argument against trying. It is an argument for understanding the full scope of what trying actually means. An interstellar mission is not a technology project. It is a civilization project. It requires not just the engineering of a ship, but the engineering of the social, institutional, and cultural structures that can sustain a multi-generational commitment to a goal with no intermediate payoff. The technical challenges of relativistic travel are formidable. The civilizational challenges of any interstellar travel may be comparable. The history of human understanding of the speed of light is itself a story that matters. We have known the speed of light is finite since the 17th century. In 1676, the Danish astronomer Ole Romer noticed that the timing of Jupiter's moon's eclipses varied depending on whether Earth was moving toward or away from Jupiter. He correctly attributed the variation to the finite travel time of light. His estimate of the speed of light was about 137,000 miles per second, about 25% too slow by modern measurements, but qualitatively correct. For more than 2 centuries after that, the speed of light was known to be large but finite. It was understood to be the fastest thing observed. But it was not yet understood to be the absolute maximum speed of anything. That understanding came only with Einstein in 1905. Before special relativity, there was no theoretical reason why a particle with enough energy couldn't go faster than light. Maxwell's equations predicted the speed of light, but Newtonian mechanics didn't forbid exceeding it. The resolution of this tension was Einstein's insight that the inconsistency wasn't in Maxwell's equations. It was in the Newtonian assumption that space and time are absolute. The 120 years since then have been a continuous process of deeper understanding of what the speed of light as an absolute limit actually means. We now understand it is not just the speed of light propagation. It is the speed of causality propagation, the maximum rate at which any influence can travel from any cause to any effect, the enforcement mechanism for the arrow of time, the structural reason the universe has a consistent past and future rather than a jumble of causally disconnected events. This understanding has been hard-won through experiment, theory, and the slow reconciliation of relativity with quantum mechanics. It has survived every test. Every attempt to find a faster-than-light signal, from quantum entanglement to exotic matter proposals to wormhole shortcuts, has either failed or turned out on closer examination not to actually transmit information faster than light. The universe is consistent. It enforces its own rules at every level, and its rules, at the level relevant to starship design, say, not at light speed. That is the most precisely tested statement in physics. It is as close to a certainty as human knowledge can get. There is another physical effect that strikes specifically at the crew's ability to function, and it's one that most discussions of interstellar travel treat only superficially. Solar particle events, the sudden releases of charged particles from stellar eruptions, are hazardous in ways that extend beyond the gradual accumulation of cosmic ray damage. Our own sun produces these events regularly. Solar flares, sudden releases of electromagnetic energy and accelerated particles. Coronal mass ejections, massive eruptions of plasma and magnetic field from the solar corona. Solar energetic particle events, which can bathe the inner solar system in high-energy protons within hours of a large flare. During the Apollo missions, astronauts were outside Earth's magnetosphere during transit to and from the Moon. A large solar particle event during an Apollo mission could have been catastrophic. They were fortunate that no major events occurred during any of the lunar surface stays. A single large solar energetic particle event can deliver radiation doses of several sieverts in a matter of hours. Above 1 sievert in a short period, acute radiation syndrome begins. Nausea, vomiting, fatigue. Above about 3 to 4 sieverts, without treatment, there is significant probability of being gone within weeks from bone marrow failure. Above 6 sieverts, survival is unlikely even with intensive medical intervention. Astronauts on a relativistic journey would be exposed to the galactic cosmic ray background continuously. They would also be at risk from any stellar energetic particle events they pass near en route. The Sun's particle events are generated by magnetic reconnection in the solar corona. Every star that produces magnetic activity produces similar events. The path between stars is not uniform. It is not a featureless void. It is a region traversed by the outflows of multiple stars, by the remnants of stellar winds, by variations in the local magnetic field that influence cosmic ray flux. An unlucky passage through a region with elevated particle density, or timing an encounter with a stellar energetic particle event from a nearby star, could deliver acute radiation doses that overwhelm even the best shielding. Inside a spacecraft whose shielding is already compromised by years of hull erosion, the consequences could be severe. The medical resources to treat acute radiation syndrome, which requires blood transfusions, bone marrow stimulating factors, and intensive supportive care over weeks, may be severely limited on a spacecraft that has been traveling for years. And acute radiation syndrome in a crew member represents not just a human medical emergency, it is an operational crisis. The crew is small. Every member is needed. The loss of any individual to incapacitation degrades the mission's ability to manage emergencies, maintain critical systems, and make sound decisions. Small crews have no redundancy. There is no backup person waiting to fill a critical role. The mission architecture depends on every crew member remaining functional. Any event that removes even one person from full functionality threatens the mission in ways that become worse as the journey lengthens. The biological rhythm disruption that comes with extended deep space travel is more subtle than bone loss or radiation damage, but it compounds the other problems. Human biology runs on circadian rhythms, roughly 24-hour cycles that synchronize dozens of physiological processes. Cortisol levels, melatonin production, body temperature, heart rate and blood pressure, immune function, sleep architecture. All of these follow daily cycles that are entrained by environmental cues, primarily light, but also social interaction, activity patterns, and temperature variation. In a spacecraft traveling between stars, the environmental cues for circadian rhythm maintenance are artificial. The light cycle is provided by the ship's lighting system, which can be programmed to simulate Earth's day-night pattern. But the programming is only as good as the understanding of what the crew needs, and what they need drifts over time as the body adapts to the artificial environment. Circadian disruption has documented effects on health. Shift workers, who chronically violate their circadian rhythms, have elevated rates of cancer, metabolic syndrome, cardiovascular disease, and cognitive impairment compared to day workers. The mechanisms involve disrupted repair processes that normally occur during sleep, altered immune function, and dysregulation of the metabolic hormones that govern energy use. On a spacecraft, the light environment can be controlled, but other circadian cues are harder to manage. The gravitational environment, if the ship is rotating for simulated gravity, may have its own temporal pattern due to the structure of the ship. Meal timing, which is a strong circadian cue, may be governed by operational necessities rather than biological needs. The social schedule of a small crew managing a complex ship may impose patterns that conflict with optimal circadian alignment. Over months and years, the cumulative effect of imperfect circadian alignment adds to the other biological stresses. The immune suppression associated with circadian disruption compounds the immune effects of radiation exposure and the psychological stress of isolation. The cognitive impairment associated with poor sleep, which is itself associated with disrupted circadian rhythm, compounds the neurological damage from cosmic ray exposure. The metabolic dysfunction associated with chronic circadian disruption adds to the cardiovascular remodeling from weightlessness. None of these interactions are simple. None of them are fully understood, even from studying astronauts in low Earth orbit, where the missions are shorter and the environmental control is better understood. The crew of a relativistic spacecraft would be navigating a biological minefield with incomplete maps. There is one more consideration that has not been discussed, and it concerns what happens if something goes wrong inside the ship rather than outside it. A relativistic spacecraft is not a replacement for Earth. It is a closed ecological system of finite size and finite resources, isolated from any resupply, on a trajectory that cannot be easily changed once underway. Every kilogram of water aboard must be recycled because there is no source of new water. Every kilogram of food must either be grown aboard or stored at departure because there is no resupply. Every breath of oxygen must be produced by the life support systems because there is no source of new oxygen beyond what is cycled from the carbon dioxide the crew exhales. If the water recycling system fails and cannot be repaired with available parts, the crew has, however many days of reserve water, exist in the backup tanks. If the oxygen generation system fails and cannot be repaired, the crew has, however many hours, of reserve air remain. If the food production systems fail, the crew has, however many months, of emergency rations were loaded at departure. These are not hypothetical concerns. They are engineering realities. Systems fail. All systems fail, eventually given enough time. A spacecraft designed for a multi-decade mission must be designed with failure modes in mind. Every critical system needs redundancy. Every redundant system needs its own maintenance regime. Every maintenance regime requires crew time, consumables, and spare parts that must be carried from the beginning. The spare parts for a multi-decade mission are themselves a significant mass burden. Spare parts for every critical system. More spare parts for the systems most likely to fail. Spare parts for the first set of spares. Because there is no resupply. When the last spare for a critical system is used and the system fails again, the crew must improvise a solution with whatever is available. The history of long-duration spaceflight, even in low Earth orbit where resupply missions can arrive in days, is full of examples of systems failing unexpectedly and requiring creative solutions. Clogged filters, failed pumps, degraded batteries, malfunctioning computers, leaking seals. All of these have occurred on the International Space Station. All were resolved because resupply was available, because specialists on the ground could be consulted in real time, because additional crew members and equipment could be launched if needed. On a relativistic interstellar spacecraft, none of those lifelines exist. The crew is self-contained. What they brought is what they have. Their ability to improvise, to repair, to jury-rig solutions to unexpected failures is not just a nice quality. It is a survival requirement. And it is a quality that must be maintained not just at departure, but throughout a journey that systematically degrades the physical and cognitive capabilities of everyone aboard. The question of communication with Earth, already touched on briefly, deserves deeper examination for what it means operationally. At the speed of light, a signal takes 4.24 years to travel from Earth to the nearest star, Proxima Centauri. A ship traveling to Proxima Centauri at 90% of light speed would, from Earth's perspective, be sending back signals that take progressively longer to arrive as the distance increases. A message sent from Earth 1 year into the mission must travel to wherever the ship then is and then keep traveling to catch the ship, which is still moving away at 90% of light speed. The message gains on the ship at only 10% of the speed of light. A ship that has traveled 0.9 light-years in 1 year takes 9 years of additional travel time for a message sent at that point to catch it. By year 5, the message lag is 45 years. By the time the ship nears Proxima Centauri, a message sent from Earth will take decades to arrive, and a reply will take decades more. For the crew, who experience compressed subjective time, the delays in Earth's side of communication grow even more confusing. Messages sent by Earth during the early mission arrive at the ship during the crew's early voyage. Messages sent by Earth during years when the crew is experiencing. Only months arrive at the ship, weeks of crew time after the Earth time messages were composed. The communication is not just delayed. It is temporally jumbled from the crew's perspective. Earth is sending messages across decades of its time that the crew receives compressed into subjective months. The bandwidth of the communication link, already limited by the power of the transmitters and the area of the receiving antenna, decreases as distance increases. A transmitter of fixed power produces a signal that spreads in area as the inverse square of distance. Double the distance, and the signal strength at the receiver drops to 1/4. At the distance of Proxima Centauri, even a high-power transmitter using a large dish antenna produces a signal that requires a large receiving antenna to detect. The ship's receiving antenna is limited in size by mass constraints. As the distance grows throughout the journey, the signal weakens and the effective data rate of the communication link drops. By the time the ship is mid-journey, the link may be capable of transmitting only compressed summaries, not full telemetry. By the time of arrival, the link may be barely sufficient for brief messages. Mission-critical decisions, any situation that requires input from Earth expertise, cannot wait for a 4-plus-year round-trip communication time. The crew must make all significant decisions on their own. They must have the knowledge, skills, and judgment to handle any situation that arises without consultation. They must maintain documentation and institutional knowledge aboard the ship sufficient to inform those decisions without any direct contact with Earth's expertise. This places extraordinary demands on crew selection and training. Every crew member must be capable of performing roles beyond their primary specialty. The mission cannot succeed if any critical knowledge resides only in a single person who might be incapacitated. Cross-training, redundancy of expertise, and thorough documentation of every system and procedure are operational necessities. All of this preparation must be carried out, and then maintained across years or decades of use, without external support. The crew of a relativistic spacecraft is not supported by Earth. It is, in every practical sense, on its own. What does the actual timeline of research on these questions look like, and where does it leave us now? The 20th century saw an enormous growth in understanding of what deep space travel actually involves. In the 1940s and 50s, early space program planning was dominated by what might charitably be called optimism, unconstrained by physics. Documents from those years speak of manned flights to the nearest stars within a few generations. The numbers were not checked carefully against what propulsion technology could actually deliver. They were more aspirational than analytical. The 1960s brought sober accounting. The rocket equation was applied honestly to interstellar distances. The conclusions were sobering. Nuclear propulsion, which had been seriously studied under programs like Project Orion, which proposed spacecraft propelled by nuclear bomb detonations, could potentially reach a few percent of light speed. A few percent of light speed to the nearest star is still a journey of over a century. The Project Orion engineering was sound. The physics worked. The social and political challenges, specifically the requirement to detonate thousands of nuclear weapons in space or near Earth, made it a non-starter outside of the most extreme circumstances. Later, in the 1960s and 70s, the British Interplanetary Society produced the Project Daedalus study. This was a serious, detailed engineering analysis of a fusion-powered unmanned probe that could reach Barnard's star, about 6 light-years from Earth, in roughly 50 years. Barnard's star was chosen because it was at the time believed to have a planetary system, though this was later disputed. Project Daedalus used helium-3 and deuterium fusion as its propellant. It proposed a 2-stage vehicle with a total initial mass of about 54,000 tons. The payload at the destination, the scientific instruments and communications system, would mass about 450 tons, less than 1% of the total departure mass. The rest was fuel. The engineering was detailed. The conclusions were sound. The mission was achievable in principle. The barriers were practical rather than fundamental. The required helium-3, the fusion fuel, is extremely rare on Earth, but abundant on the Moon and in the outer solar system. Obtaining it in sufficient quantities would require a space industry far beyond what existed in the 1970s. The controlled fusion reactions needed for the drive had not been achieved even in stationary power plants. Project Daedalus was a demonstration that interstellar travel was not prohibited by physics, but a description of what making it real would actually require. More recent proposals have extended and refined this kind of thinking. Breakthrough Starshot, announced in 2016 by a group including the late Stephen Hawking and funded by Yuri Milner, proposed sending gram-scale probes to Alpha Centauri at 20% of light speed, using ground-based laser arrays. The probes would carry minimal instrumentation. They would fly through the system rather than stopping. They would transmit data back at the speed of light. The mission would take about 20 years for the probe to arrive, plus 4.2 years for the data to return. Total delay from launch to first data, roughly 25 years. The engineering challenges are real. Building a laser array capable of delivering the required power to a small sail at interstellar distances. Constructing a sail that can survive the acceleration phase without melting or tearing. Designing electronics small enough and light enough to fit in a gram-scale package while surviving the radiation environment of a 20-year journey at relativistic speed. None of these are solved, but none of them violate fundamental physics. They are engineering problems. Starshot represents the most serious current proposal for actually reaching another star system with a physical object. It has no crew. It would provide limited scientific data compared to a crewed mission. It would not establish any permanent presence. But it would prove that interstellar transit is achievable, that a physical object built on Earth can cross the void to another star and send back information. That milestone, modest as it sounds, has never been reached. The furthest human-built objects, the Voyager probes, have only just crossed into interstellar space after nearly 50 years of travel, and are still less than a single light day from Earth. Reaching the nearest star with a physical object in a human-relevant timescale would be a milestone with no precedent. It would be the first step, not the destination. But the first step is always the one that proves the path is real. After Starshot, if it succeeds, the next steps become clearer. Larger, unmanned probes. Probes with the ability to orbit or decelerate at the destination. Probes with more sophisticated instrumentation. Eventually, probes with the ability to transmit not just data, but processed information about what they find. And eventually, over timescales that no one alive today can specify with confidence, the question of crewed interstellar travel. Not at light speed. Not in comfort. Not quickly. But not never. The history of the speed of light as a fundamental limit, from Romer's first measurement in 1676 to Einstein's theoretical unification to a century of experimental confirmation, is a history of increasing precision and increasing understanding. We know more about what the limit means now than we did in 1905. We understand its connection to causality, to the structure of space-time, to the behavior of quantum fields in the vicinity of horizons, in ways that were not accessible to Einstein himself. That understanding does not change the limit, but it deepens the appreciation of why it exists. And it makes clear that light-speed travel is not a door that will eventually open with the right key. It is a wall that is part of the architecture. What's behind the wall is not a faster universe. It is a universe with a different structure, and that universe does not contain us or anything else we recognize. The universe we have, with its speed limits and its causality and its patience across billions of years, contains everything we are and everything we might someday reach. At the speeds it allows. On the timescales it demands. With the costs it imposes. That is the deal. And understanding the full terms of that deal every physical detail of why light-speed travel would destroy you before you arrived anywhere, is the beginning of engaging honestly with what reaching the stars would actually require. Not the dream version, the real one. Tonight, across the physics of time dilation and length contraction and relativistic mass, across the particle flux and the blue-shifted radiation and the cosmic ray bombardment and the cascading engineering failures, what you've seen is the honest answer to why light-speed travel would destroy you before you arrived anywhere. It's not a story about a single obstacle. It's a story about a cascade, each problem enabling others, each solution making neighboring problems worse. The interstellar medium that becomes a particle beam, the cosmic background that becomes a gamma-ray wall, the Lorentz factor that makes every kilogram of ship harder and harder and eventually infinitely hard to push faster. The crew being simultaneously eroded by radiation, weakened by weightlessness, cognitively impaired by cosmic ray bombardment, and severed from everyone they knew by an asymmetric river of time. The propellant requirements that exceed everything civilization has ever produced by orders of magnitude. This is what light-speed travel actually is. Not an adventure, not a threshold waiting to be crossed. A physical reality that the universe enforces through every mechanism available to it. The speed of light is not a record. It is not a barrier that will fall to a better engine. It is the speed at which the universe itself propagates information. The speed of cause and effect. The enforcer of the arrow of time. The reason complex structures, chemistry, life, and minds can exist at all. And the next time you look up at the stars, at those patient ancient lights hanging overhead, understand what you're seeing. Not destinations waiting to be visited on a casual afternoon. Not a universe that's on your side. A universe that is what it is. Structured by laws, it enforces without exception, offering travel among the stars at a price far higher than the dream ever acknowledged. Slow, costly, dangerous, demanding, and ultimately, for those willing to pay the price honestly, possible. Just not at the speed of light. Never at the speed of light. If this changed how you think about the distance between here and the nearest star, about what physics is actually telling us when we look up at the night sky, take a second to like the video or subscribe. It helps us keep making these honest, unsparing dives into what the universe actually is. The cosmos is patient. It has been here for 13.8 billion years. It will be here long after any individual attempt to cross it. Good night.